Hello everyone, welcome back to AA Academy. So let's continue the model question paper of Introduction to Electrical Engineering for Module 4, that is for transformers and three-phase induction motor. Let's move on to the question paper. Question number 7, Module 4. First one, derive EMF equation of a transformer and hence obtain the voltage and current transformation ratios for 8 marks. So to derive the EMF equation of transformer, you need to draw a sinusoidal waveform. If you're not drawing the waveform, just simply writing the derivation means, so you might have lose the marks. So that let us consider the notations for this EMF equation of transformer. So let consider a transformer has number of turns, whereas 1 indicates primary, so that N1 is nothing but number of turns in primary winding. Similarly, N2 is number of turns in secondary winding. Then we define phi M is nothing but flux M, maximum flux in core in terms of Weber, whereas it is given with the help of the relationship of maximum flux density and area of cross section, so that phi m is given by bm into A. Similarly, F is nothing but frequency of AC supply in hertz. So now we can see the waveform. So to complete one full waveform, it takes one time period. So just observe here the flux. So considering the flux waveform, so that the flux which is started from 0 and it finishes its half cycle for 180 degree, and again it continues in a negative half cycle and it finishes its full cycle for 2 pi. So that from where the flux which is maximum at 90 degree, that is at pi by 2, the flux which will be maximum pi m 0 to pi by 2, so that you can observe this waveform. So here the flux that is sinusoidally increases to its maximum value from 0 to pi by 2 to reach phi m, so that its maximum value in one quarter of the cycle is 1 by 4f. You know that t is given by 1 by f. For 1 by 4, the time is nothing but 1 by 4 into f to reach maximum flux density, sorry, maximum flux phi m. So now you define average rate of change of flux with the help of Faraday's law of electromagnetic induction. Where there is a flux, also where there is a EMF, there is a flux. So with the help of that, so now the average rate of change of flux is nothing but d phi by dt, whereas d phi change in flux from minimum to maximum, that is 0 to pi m, so that d phi is nothing but, so right here d phi is nothing but 0 change in flux from 0 to maximum, that is final value is pi m minus 0, that is nothing but pi m itself, d phi, so that you're writing d phi equals to pi m, whereas dt is nothing but time taken to reach maximum flux. So how much time it takes to reach maximum flux pi m, that is 1 by 4f, so that dt is 1 by 4f, so that you're rewriting it as 4 into f into pi m, and you're giving this as equation number 1. So now we are defining induced EMF per turn according to Faraday's law of electromagnetic induction. Where there is a EMF, there is a flux. So that induced EMF per turn equals rate of change of flux per turn. Therefore, you can rewrite average EMF per turn equals 4 into F into pi m in terms of volts. So now you define form factor, whereas a form factor of an alternating voltage is given by RMS value of an alternating voltage to the average value of an alternating voltage. So with the help of that, so we have average EMF per turn, but we should write in the form of RMS value, so that RMS value of an alternating voltage is given by form factor into average value. So that form factor value is 1.11 and average value is nothing but 4 into f into pi m. We can get 4.44 f into pi m. So next you need to write the EMF equations for primary side winding and secondary side winding, so that RMS value of an induced EMF in a primary winding is denoted by E1. So that E1 is given by, again, RMS value of EMF per turn into number of turns in primary winding. So you can get induced EMF. EMF equation of transformer in primary winding is given by 4.44 F into pi m into N1, whereas N1 is number of turns in primary winding and E1 is EMF that produced it, EMF produced, or else voltage across primary winding. Similarly, RMS induced EMF in secondary winding E2 is given by 4.44 F pi m into N2. So if you consider the ideal transformer on low load condition, the induced EMF and supply voltage that will be same, and induced EMF and voltage across the load is also same. So that you can write here E1 equals to V1, E2 equals to V2. Ideal transformer is nothing but the transformer which has 100% of efficiency, whereas it doesn't have any losses. There is no losses in ideal transformer, and always input power that will be same as output power. So with the help of that, in a question they asked you to write the voltage and current relations, that is a transformation ratio, so that you are defining the ideal transformer where the input power that is same as output power and there is no losses. So I can rewrite input power equals to output power. Input power is nothing but V1 I1 and output power is nothing but V2 I2. With the help of this relationship, you are writing here as V1 or E1. Okay, so that you can rewrite here. Therefore, V2 by V1, this is not right. V2 by V1 equals to I1 by I2. It is nothing but transformation ratio K. So this is not right, E1 by E2. So actually it is E2 by E1. So V2 by V1 equals to I1 by I2, that is equals to K. It is nothing but transformation ratio. They asked it for 8 marks. So to write these equations, you have 2 marks. Okay. And for the derivation of transformer, you have some 6 marks. So you have to draw the waveform. For waveform, you have 1 mark. For the derivation, 5 marks. Okay. First, you define the notation. Then you define rate of change of flux d phi by dt, whereas d phi is pi m, dt is 1 by 4f. Then you define average induced EMF per turn, that is nothing but 4.44, sorry, that is nothing but 4 into f into pi m. So after that, you define form factor. With the help of that, define RMS value, that is 4.44 f into pi m. For primary winding side, you are multiplying by N1. For secondary winding side, you are multiplying by N2. So that E1 is 4.44 F into phi m into N1. Similarly, for secondary side, 4.44 F into phi m into N2. Okay. So similarly for transformation ratio, so you're considering the ideal transformer. With the help of that, what you're doing, input power equals to output power. So that V1 I1 equals to V2 I2. So you're writing V2 by V1 equals to I1 by I2. That you are defining as transformation ratio is nothing but K. Okay. So look into the second question. They asked you to write types of, just see the question. So what they asked, with a neat diagram, sorry. With a neat diagram, explain the types of three-phase induction motors. So there are 2 types of induction motor. One is squirrel cage induction motor, other one is slip ring induction motor. So diagram, it is having a weightage of marks, so that you should write the diagram neatly. 2 types of induction motors. One is squirrel cage induction motor, another one is slip ring induction motor. So what do you mean by squirrel cage induction motor? The entire structure which looks like cage, so that you can call this as squirrel cage induction motor. And it is having end rings, you can observe. This squirrel cage induction motor is having end rings. And each end rings which are shorted with the help of bars. These end rings which are shorted with the help of bars. So that bars you can call it as copper or aluminum bars. And that bars which are always uninsulated bars. You're shorting the end rings with the help of uninsulated copper or aluminum bars. So the entire structure which looks like cage, you can call this as squirrel case induction motor. So you can see here that rotor core is cylindrical. The rotor core is cylindrical and slotted on its periphery, so that the rotor, which consists of what? As I told, it is having a bar, is nothing but the rotor which consists of uninsulated copper or aluminum bars called rotor conductors. And the bars are placed in the slots, the bars which are placed in the slots, and these bars are permanently shorted each end with the help of conducting copper ring. You can call that conducting copper ring as end rings. So in general, the end rings which are short circuited with the help of uninsulated copper or aluminum bars. Hence, the entire structure, which looks like case, forming a closed electrical circuit. So the rotor is called squirrel case rotor or squirrel case induction motor. So as the bars which are permanently shorted to each other through end rings, so that the entire rotor resistance is very, very small. If the bar which is shorted with the help of end rings, what happens? The rotor resistance, whatever the resistance which has in a rotor, it is very, very small. Hence, this rotor is also called short circuited rotor. The end rings which are permanently shorted with the help of uninsulated copper or aluminum bars. So that another name for this is short circuited rotor. And the second case, here you will be not using any of the external resistance, and that can be introduced in a rotor circuit. Hence the construction of this type of motor, which looks very simple. And you need to write these points in the examination for 3 and 3 marks. Total marks is 6. 3 marks is for squirrel case induction motor, and the 3 marks is for slip ring induction motor. For the squirrel case induction motor, 1 or 1.5 marks for circuit or else the diagram. So, and also for the explanation, you may get 2 marks. So you need to write these 6 points. These points are more than sufficient to write in the exam. Okay. And the next is a slip ring or phase wound induction motor. Slip ring or phase wound induction motor. Second case. So you can see here it is having, you just observe the diagram. So here what happened? So you'll be having the rotor winding. See, the rotor winding which is connected in star, and each end of this winding which is connected to slip rings. You can see each end of the phase which is connected to slip ring, and another end of this slip ring is connected to external star connected rheostat, and which is short circuited, and the entire combination is supported by short, and the slip ring at the end, it is having a brushes. So now you can see the points. In this type of construction, the rotor winding is exactly similar to stator. Means if the stator is star connected, the rotor which is also star connected. If the stator is delta connected, the rotor also which will be connected in delta. So that the rotor construction, that is the lamination, whenever the lamination which comes, the rotor construction is laminated and slotted, and each slot which contains the rotor winding and 3 ends of, as whatever I explained in a diagram, the same thing you're writing. 3 ends of these 3 phase winding, where you're connecting it to the slip rings, either star or delta, which are permanently connected. So after that, what, with the help of slip ring, the external resistance will be adding at the end of slip ring in series with each phase of rotor winding, and these resistances are short circuited. So by this way, the value of rotor resistances per phase can be controlled. So in practical applications, we prefer more squirrel case induction motor than slip ring induction motor. Okay. So these are the points you need to write in the examination. The diagram, explanation. 2 types of induction motor. One is squirrel case induction motor, other one is slip ring induction motor. In the slip ring induction motor, the stator winding which is either connected in star or delta. Rotor and stator will be following the same construction, and end of each phase is connected to the slip rings. Another end of slip ring which is connected to the external star connected rheostat. So to control the value of rotor resistance. And the next is a transformer, a problem they asked. A transformer, this is for again 8, I guess, 8, 6, 8. Okay, you just see 868, not 868. So just see the question paper, the model question paper. So here what happened? They asked question number 7A is for 8 marks. Question number 7B is for 6 marks. And again C is for 8 marks. The problem is for 8 marks, 4 points. Each point is having 2 marks. Okay, so let us solve the problem of transformer. So before solving the numerical, as I told, you guys should understand the numerical properly, then you will be able to solve it neatly. So what they asked, a transformer which is rated at 100 kVA. They given kVA rating, that is 100, and they're given at full load. At full load, so at full load, what they're given, there will be a copper loss, that is PCU. Copper loss is 1200 watt, and there will be iron loss, that is PI is 960 watt. And they asked you to find, first point, calculate the efficiency at full load. Eta FL you need to find. Efficiency at full load when the power factor is unity, UPF. And second case again, at half load, pointed power factor. Then load kVA at which maximum efficiency will occur. After that, maximum efficiency we'll get to know later. First point, C now. At full load. Before that, what you need to do? You need to write the common equation for efficiency. Eta is given by for any load. X is nothing but load. X into kVA rating. X into, one second, I'll rewrite. For efficiency formulae, so you need to write eta equals to X into kVA rating into power factor divided by X into kVA rating into power factor plus total losses. So that eta is given by X into kVA rating into power factor, that is nothing but cos pi, divided by X into kVA into power factor plus iron loss plus x square into copper loss. You're writing efficiency in terms of 100, so that multiplied by 100. So for full load, what is the value of x? X is 1 for full load. So just substitute this formula, so that eta full load is given by X is 1 into kVA rating is 100, that is 100 into 10 to the power 3 k in terms of VA you are writing, into power factor is 1 divided by again 1 into 100 into 10 to the power 3 into power factor is 1 plus iron loss is 960 watt plus x square is nothing but 1 square into copper loss is 1200 watt. You can get eta full load, that is nothing but, one second, I'll calculate. 1 into 100 into 10 to the power 3, that is 100 kilo divided by 100 kilo plus 960 plus 1200. So you can get 97.88 percentage. 97.88. 97.88 percentage for full load. Similarly, what they asked for the second case, they asked you to find it for half load. So half load is nothing but x is nothing but half for half load. Eta half load you need to find. for x equals to half is nothing but 0.5. And power factor cos phi of 0.8. Same formula, you need to substitute the value of x and power factor. So how will you find for half load, eta half load equals x is 0.5 now, 0.5 into 100 into 10 to the power 3 into power factor is 0.8 whole divided by output plus losses. 0.5 into 100 into 10 to the power 3 into 0.8 plus 960 plus x square is nothing but 0.5 square into 1200 multiplied by 100. So by substituting these, you need to substitute it well, then only you can get right answer. Don't do any mistakes while doing substitution. Okay. So you can write 0.5 into 100 kilo into 0.8 divided by plus 960 plus 0.25 0.5 sorry 0.5 square into 1200. So you can get 96.94 percentage. So eta half load is nothing but 96.94 percentage. You can verify the answer. If you're getting any wrong answer, please write in a comment box. Okay. 2 points finished. What is the third point? The load kVA at which maximum efficiency will occur. Load kVA, third point. So third point is nothing but load kVA. There is a formula for load kVA. So load kVA, which is given by load kVA, third point. Load kVA is given by at maximum efficiency. Remember, load kVA at maximum efficiency. Load kVA at eta max means while finding the maximum efficiency, you need to enter the value of kVA, whatever you're getting in a 0.3. So it is given by kVA rating into square root of Pi divided by PCU. Pi divided by PCU. So now what is the value of kVA here? 100. Anyhow, output you are writing in terms of kVA only, so that no need to multiply by into 10 to the power 3. 100 into square root of Pi is nothing but 960 divided by 1200. You can get 960 divided by 1200 into 100. You get 89.44 kVA. 89.44 kVA. For this value, you need to find the value of maximum efficiency. That is for fourth point. So fourth point, what they asked? They asked you to find the maximum efficiency, eta max. The maximum efficiency is given by kVA rating into power factor x kVA rating into power factor divided by anyhow it is for full load only always, so that you no need to write value of x, you no need to write x. Okay, kVA into cos phi plus 2 into Pi. Condition for maximum efficiency is Pi equals to PC. So that you can rewrite here 2 Pi. So what is the kVA at maximum efficiency now? 89.44. Remember, 89.44 into 10 to the power 3. At power factor, what they asked? At power factor of 0.85, sorry, 0.85 divided by 89.44 into 10 to the power 3 into 0.85 plus 2 into, remember, Pi equals to PCU. If they are given the value of copper loss and iron loss, you should always write 2 into Pi while solving the maximum efficiency problem. So that 2 into what is the value of Pi? 960. Then we get the value of maximum efficiency, eta max. So 89.44 kilo into 0.85 divided by answer plus 2 into 960. You get 97.53 percentage. 97.53 percentage. This is the solution. So 4 points. So you can expect each point is having 2 marks. So what they asked, understand the question properly. So they are given the value of copper loss, iron loss, and kVA rating. They asked you to find efficiency at half load and full load for UPF and 0.8 power factor. Use the common formula. Then you can get eta full load, eta half load. For full load, the value of X is 1. For half load, the value of X is 0.5. Like that, if they change it to 60 percentage, 0.6, 70 percentage, 0.7, 85 percentage, 0.8, the value of loads. Okay. Similarly, a third point load kVA you are calculating, then the same load kVA for maximum efficiency, they mentioned it clearly so that whenever you are solving the maximum efficiency, particularly for this problem, you need to enter the value of kVA as 89.44 kVA. So these are the solution of module 4. If you are having any doubts regarding this, feel free to write in a comment box. So that I hope you're understanding the concept. Thank you so much. If you like this video, please do subscribe. Thank you. Have a nice day.